All right, we're going to look at solving trigonometric equations. And so whenever we have an equation that involves some trigonometric function to it, we want to find all the values that would make it true. And so we're going to be combining what we know about solving equations with what we know about inverse trig to get these solutions. So to solve a trigonometric equation, we use the rules of algebra to isolate the trigonometric function on one side of the equal sign. Then we use our knowledge of the values of inverse trigonometric functions to solve for the variable. So for example 1, what we need to get alone is the sine x. Excuse me. So I want to add 1 onto both sides. So I'm left with 2 times sine of x equals 1. Sine of x has this 2 being multiplied, that coefficient there, so I'm going to divide both sides by that coefficient. So I'm left with sine of x equals 1/2. Now what we can do to get rid of sine, we need to take the inverse, which is arcsine, of both sides of our equation. So arcsine of the left and arcsine of the right. What happens is arcsine and sine are inverses of each other, so they cancel out. So I'm left with x equals arcsine of 1/2. So we're not done yet because we don't have our solutions, but we're going to pause for a second and talk about what this means. So previously, when asked to only simplify arcsine of 1/2, because that's what we have up here, that's what we're going to be talking about, we only considered the right half of the unit circle. So arcsine and arctangent, we looked at the right side, and then arccosine, we looked at the top. Now this is because we were doing it for inverse functions and we could only have one solution. However, when we are solving this problem or when we're solving equations, we want to find all of the solutions that are in the solution set. So we have to consider the entire unit circle and anything outside of that, so any coterminal angles as well. So if we're trying to figure out arcsine of 1/2, we want to look at our unit circle and find what angles have a sine value of 1/2. So sine is my y, so I have one right here at pi/6. And my other one is here at 5 pi/6. So back to our notes, we know our two solutions are going to be at pi/6 and 5 pi/6. Now, I'm going to scoot this up a little bit. I'm going to keep that top part there. So we want all of the solutions. So if we look at this picture here, we do have a solution at pi/6. We have a solution at 5 pi/6, but there are a lot more than that. There's one at -7 pi/6. There's one here at 13 pi/6. And there's going to be infinite number of solutions because we know that our curve goes on forever. So we want to include all of those. So to do that, we know that we can continue adding 2 pi because both sine and cosine have a natural period of 2 pi. So we can add 2 pi one time, we could add it 2 times, 3 times, 4 times, 5 times, even k times, where k is an integer. So for our final answers, I'm going to scoot this up a little bit further. So when we were doing arcsine of 1/2, we would say pi/6 plus, we're adding k times the period, but when we do k times our period, we like the 2 in front and then pi at the end, so we kind of stick k in between the 2 pi from our period. So we have pi over 6 plus 2k pi and 5 pi over 6 plus 2k pi. And that will include all of the coterminal angles, whether they're positive or negative, because k is an integer. And that way we get all of our solutions. So I'm going to highlight this because it's our answer. That and that. And you have to have both to get full credit. All right, we're going to flip our page. All right, so looking at example 2, it looks a little different here. It says find all the solutions to the equation tangent squared minus 3 equals 0. It's a little different because this time we have tangent, but we also have it being squared, and so that's going to change how we complete this problem a little bit. So to start, I have to get tangent squared by itself, so I'm going to add 3 onto both sides. So I have tangent squared x equals positive 3. Well, I don't want tangent squared, I just want tangent. So to get rid of that square, I need to take the square root of both sides. So we're going to make a little note here. We're going to take the square root of both sides. Not as thin as I wanted it. So when I take the square root of the left, I would have, I'm actually just going to rewrite it. So let's do square root. When I do square root of tangent squared, I'm left with tangent. When I do the square root of 3, I actually get positive or negative square root of 3, because I can have a positive answer or a negative answer anytime I do the square root. So when we do this, now we have two answers. We need to split this into two separate problems. So I'm going to rewrite on the left, tangent of x equals positive square root of 3. And on the right, I'm going to write tangent of x equals negative square root of 3. And I need to solve both of these so that I can include all of my solutions in the solution set. So to get rid of tangent, I have to take arctangent of both sides. So I'm going to do arctangent of the left and arctangent of the right. Well, arctangent of tangent cancels out, so I have x equals arctangent of positive square root of 3. And I'm actually going to finish this one before going to the next one. So I want to know what angles on my unit circle have a tangent value of square root of 3. So positive square root of 3. So looking at my unit circle, I have a tangent of square root of 3 here at pi over 3. I also have one down here at 4 pi over 3. So I have pi over 3 and 4 pi over 3. So I have x equals pi over 3 and 4 pi over 3. I'm not done with those yet because we want to include all the solutions, so we do have to add something onto each of those. But for now, I want to finish solving this one. So for this, I take arctangent of both sides. I'm going to write it again. So arctangent of the left, arctangent of the right. So I have x equals arctangent of negative square root of 3. So looking at my unit circle, I want to know what angles have a tangent value of negative square root of 3. So looking at the top, I have negative square root of 3 here for 2 pi over 3. And I also have it in quadrant 4 at 5 pi over 3. So 2 pi over 3 and 5 pi over 3. All right, so we have our 4 solutions, our 2 for each side. What's different about this is because our equation included tangent, and we did arctangent of both sides. Tangent has a period that's different than sine or cosine. So we want to continue to add 1 pi, not 2 pi, because tangent has a natural period of pi. So if you think back, when we found the period for tangent, it was pi over k, not 2 pi over k. So we're only adding 1 pi. So for our final solutions, I'm going to scoot it up a little bit. We have 4 of them because we had 2 for each side here. So I'm going to start with pi over 3. So pi over 3 came from here, plus I'm adding k pi onto it because pi is my natural period for tangent. 4 pi over 3 plus k pi. And I want to do the same thing for both of these. So I have 2 pi over 3 plus k pi, and 5 pi over 3 plus k pi. And that way we have all of our solutions. And I'm going to highlight those again so they stand out. So I need all 4 of these to get full credit for that question. So the bottom part kind of goes into, some of you might notice that we're a little redundant because if we write out pi over 3 plus 1 pi, that is the same thing as 4 pi over 3, but it's better to be redundant and have some repeating than to miss a solution altogether. So we do want to include all 4 on our tests. All right, let's look at example 3 here. So sometimes when we have some equations, we're going to be presented with something that has different trig expressions in it. So I have a sine squared and I have a cosine squared. That is not solvable at this moment because I can't take arc sine and arc cosine of the same thing really and have it make sense. So what I need to do is try to figure out how can I change sine squared into cosine squared so that my 2 sides match, or change cosine squared into sine squared and get them to match. So I have to change one of them somehow. To do that, we want to use what we have previously learned, like our trigonometric identities. So if there's something that contains sine squared or cosine squared that we can substitute in, we want to do that. So if you have your reference sheet, that is something that we need to use. Now, I realize I don't have one printed out, but on our reference sheet, I'm going to write it at the top here, we know that cosine squared is equal to 1 minus sine squared. That's one of our Pythagorean identities. So if I know that, I can take my 1 minus sine squared and substitute that in for cosine squared since those are equal. That way I'll have sine squared on both sides and I can go from there. So that's what I'm going to do. So I'm going to rewrite this. But instead of writing cosine squared, I'm taking that out and I'm going to put in 1 minus sine squared. Now I want to do some distributing. I want to get all my coefficients to one side and constants to one side, and then sine squareds together. So I'm going to rewrite the left side, distribute that 2 times 1 is 2, and then I have minus 2 sine squared. I want to avoid negatives if I can, so I'm going to add my 2 sine squared to both sides so I can get all of my sine squareds together. They'll cancel out on the right, so I have negative 1 plus 4 sine squared x equals 2. To get rid of that 1, I'm going to add it. So add 1 on both sides. So I have 4 sine squared x equals 3. divide both sides by 4, I get sine squared x equals 3 over 4. I have to get rid of my square. I'm going to scoot it up a little bit. Realize you can't see. So I take the square root of both sides. So I'm left with sine of x equals plus or minus the square root of 3 over 4. Now when I'm doing the square root of this fraction, I have to square root the top and the bottom number. When I square root 3, I'm going to leave it as the square root of 3 because it ends up being a decimal. When I square root my denominator, so 4, square root of 4 is 2. So I am going to split these, and when I split them, one positive, one negative, I'm going to rewrite it as the square root of 3 over 2 because that's how we change the square root of 4 into 2. So I take the arc sine on both sides, so I get x equals arc sine of, I'm going to do the positive version over here, so square root of 3 over 2. On this side, I'm going to do x equals arc sine of negative square root of 3 over 2. And so this statement here, I probably shouldn't have put there, but it's kind of in words of what I just said. So we know that sine of x is equal to positive square root of 3 over 2 as well as negative square root of 3 over 2. So we do have to take arc sine on both sides. And so for now, we're going to kind of just scribble this out because it's in our way. So we're going to kind of just jump over it and continue solving down here. So if I know x is arc sine of positive square root of 3 over 2, I want to know what angles have a sine value of that. So sine is y. Square root of 3 over 2, and that angle is pi over 3. I have another one, positive square root of 3 over 2 at 2 pi over 3. So I have two solutions so far. So we're going to say x equals pi over 3, and then x equals 2 pi over 3. And I wanted to do them separately because we know that we do have to add something onto it. So I'm going to add my 2k pi, and the reason I'm adding the 2k pi is because this time I had sine and cosine, right? So I changed my cosine squared into sine. So for sine, there's a natural period of 2 pi, and then the other one was tangent. So I have this as a solution, this as a solution, and then for the other side here, we're going to do arc sine of negative square root of 3 over 2. So a y value of negative square root of 3 over 2, I got one here at 4 pi over 3, and one here at 5 pi over 3. So we know x equals 4 pi over 3 plus 2k pi, and 5 pi over 3 plus 2k pi. If you forget that 2k pi, you will not get credit for any of the work that you do. And so I'm just going to rewrite these solutions down here so we have them all in the same place. So we have pi over 3 plus 2k pi, 2 pi over 3 plus 2k pi, oops, 4 pi over 3 plus 2k pi, and 5 pi over 3. One quick tip is if you end up taking the square root, you should have 4 solutions. In a very rare case, would you have 2? That's if you're taking the square root of like 1 or 0, probably. But otherwise, you should have 4. If you take the square root to solve, you should have 4. If there's a square root in the equation already, that's different. Then you're just treating it like a coefficient.